Hi everybody, welcome to this sixth live session. So today we are going to discuss about uh, continuity. So so first we will start some from basic problems, and then gradually we'll change the difficulty level. Okay. So yeah, so it's already 7:04 p.m. So it will be a 2-hour live session. So we shall finish at 9:04. Okay. So let's start. 1 second. Yeah. Okay, so just for sake of recall, I think it's 1 second. Just sorry for the inconvenience. Probably there is some issue with my graphic driver. Okay, so I shall reshare it. Okay, yeah. Sorry for the inconvenience caused by me. Yeah, that's fine. So I need to share it again. Yeah, yeah. So let's just shoot the definition of continuity. So yeah, let D subset of R non-empty. A map F from D to R is said to be continuous at X belongs to D. 1 second. If for any epsilon greater than 0, there will delta greater than 0, such that for any y belongs to the epsilon neighborhood of delta, equivalent to saying that this distance y minus less than delta implies mod of fx minus fy less than delta. Okay, this is the definition of continuity. So, I mean, okay, so it's a very theoretical definition. So, how to guess this definition? Okay. So, uh, okay, so we can guess it as follows. So, suppose that our I mean, our f look like this. 1 second. Suppose our f look like this, and suppose x is this point. This means what? If we choose a very small, and suppose this is fx, yeah. So this is a epsilon neighborhood of fx. Okay. And suppose this function looks like this, and if we consider this portion, then there will be we will get a small interval around x such that any point lying between this will be f of y. If we take this to be y, this to be f of y. Okay, so this is the basic intuition, the continuity. So basically a function, uh, so, Yeah. So basically, if a function, so for a function if is said to be continuous, means non-mathematically we can draw the graph of the function without lifting up the pen. Okay, that's it. So the most easiest example of the continuity is like suppose the constant maps are continuous. Why? So suppose f is a map and sorry, suppose f is a map, so suppose fx equal to k. Okay. For all x belongs to some domain D. Df means a domain of f. So intuitively it is continuous because the graph look like this. So but how to do it mathematically? So choose epsilon greater than 0. Okay. And take delta equal to epsilon. And choose any y belongs to n x epsilon. So obviously since the function f is continuous, so fy minus fx, I mean so the function f is constant, so fy minus fx equal to mod k minus k, which is 0. So which is anyway less than epsilon. So basically here any delta will work. By the way, mind the definition once again. The definition tells that for any epsilon greater than 0, we can get a delta greater than 0. I mean, this delta will may depend. So, I mean, by definition, this delta will depend on epsilon. But in some particular function, oh, wait. Can you see the screen? Can you see the screen? Logishri, can you see the screen? Please let me know. I think your mic is off. So, yeah. Can you see the screen? Hello, can you see the screen? Okay, so so the f is a continuous map, so it is anyway less than epsilon. So this mod f I minus f is equal to mod k minus k, which is 0, which is less than epsilon. Okay. So f continues at x belongs to domain of f. So can you see the screen? So the next example, well, so if you're getting some doubt or some difficulty, please let me know. Okay. So fx equal to x is continuous. So how to do it? So yeah. So choose a point, and obviously here domain and f is a map from R to R. So first choose a point from R to show f is continuous at y. Okay. Choose epsilon greater than 0. and choose delta equal epsilon. Then mod fx, then for any y belongs to neighborhood of x comma delta, which is nothing but the open interval x minus epsilon to x plus epsilon, mod fx minus fy, this is equal to mod x minus, which is less than epsilon, right? So this implies f is continuous at y. So you see this function fx equal to s is continuous at y. Similarly, the function x goes to, similarly it can be shown the function x goes to kx is continuous. Okay. So yeah, so first we have started from the definition of the continuity. Then we have shown two things. One is the continuous. First we have proved that the constant method is continuous, and secondly we have proved that the fx equal to x, this type of method continuous. Okay, so Logeshwari, please go through it once again. I shall get back to you after 2-3 minutes. In the meantime, you should go through this definition examples. Please let me know, do you have any confusion, any questions? Okay, I shall get back after 2-3 minutes. So do you have any confusion, Logeshwari? Okay. So if you have confusion at any moment, please let me know. Okay. So yeah. So well. So similarly, as a fact, what is it? One second. So as a fact, we can even show that this map x goes to x to the power continuous, and this can be proved by using the fact that product of continuous are continuous. Okay, so and since we have proved that this is continuous, and since x goes to x to the continuous for all n belongs to natural, so this together tells any polynomial function, it's a polynomial, is continuous. Okay. Also, yeah, that's it. So it's the basic thing. And secondly, well, once again, let me look at my notes. Yeah, so yeah, that's it. So let's do some problems there. So, oh yeah. So before starting the problem, there is a one important theorem. Uh, I know that the Sarah has already done this theorem in the class, but I think it's better to recall this statement of this theorem. Okay. So this theorem. Well, so before starting, so let me tell you one thing about that. Well, the definition of continuity and this theorem are going to be equivalent, and I'm sure that the sir has already proved this. Okay, but the importance of this theorem is that the definition of the definition of continuity is somehow abstract. So if suppose if we have some kind of complicated function, then using the definition, it is not always possible to show that the function is continuous. So in that situation, we need to use this theorem. And this theorem is actually the main technical tool to show that a function is not a continuous rather than to showing the function is continuous. So basically, if someone asks us to show that a function is sorry what a function is not continuous, then we need to use this theorem. So basically, this theorem is actually mostly used to show that given function is not continuous. Okay. So what is this trigonometric theorem? This theorem tells us let f b to r be a map. Okay. And obviously D is a subset of R, non-empty. Okay. Let's see belongs to D. Then if is continuous at C if and only if for every sequence xn in D converging to C, the sequence fxn will goes to fc. Okay. So this is known as the sequential criteria of the continuity. This theorem is known as the sequential criteria. Okay. Sorry. So, so basically, what is the sequential development means? Suppose a function f, and the function f is continuous as c. It means for any sequence xn in the conversion c, the corresponding sequence fxn will converge to fc. Okay. So directly using this, first let us see on one example how to show how to use it for showing the discontinuous of some function. Okay. So for example, yeah. So comes to the following example. Okay. So suppose consider f defined by fx equal to 1, x belongs to q, and 0 other. So this function, I mean, yeah, it is intuitively clear that if we wish to uh, draw the graph of the function, then it will not be a continuous graph. So it is intuitively clear that it's not continuous. So how to do it using the previous theorem? So the function is actually discontinuous at any point. Claim f is discontinuous everywhere. So how to prove it? So choose x naught belongs to. Okay. Now we know that several rationals and several irrational are dense in Q. So we know that Q bar, comma R minus Q bar. That I mean the closure of Q and R minus Q is the whole of R. So there is a sequence Rxn. There is a sequence Rn in Q, and a sequence of irrational numbers such that this R equals to x naught and I also goes to x naught. Now, if we assume that the function is continuous everywhere, then the sequential criterion, if Rn, it should goes to f. Also, if In should goes to f of x0. But since Rn are all rational, so f of Rn is equal to f of R is equal to 0. So this basically gives what? By the uniqueness of limits of the sequence, this basically gives 1 equal to 0 combination. So, so f is not continuous. So f not continuous at x naught. But since x not arbitrary, so f is continuous everywhere. Okay. So in this way we can use this theorem. So well, so just let me go through this example once again. Just wait a second. So so in this example, we have shown that the function is not continuous. Is discontinuous everywhere using a sequential criteria. So first, we have taken a point, we have taken a random point and fixed it. Now we get two sequences of rational numbers and irrational numbers which converges to x naught. And then by sequential criterion, we have finally proved the 1 equal to 0, 0, which is not possible. So if it's not continuous to x naught, since our chosen x is arbitrary, so it is discontinuous everywhere. So yeah, that's it. So yeah, so logically, please go through the example. I shall wait for 1 2 minutes. Please let me know if you have any confusion, any doubts. Okay. Yeah, so I hope that you don't have any confusion in the solution. Okay, so let's yeah, so yeah, so maybe as an example, using this above theorem. So define if x is equal to x. So the function fx will cos 1 by x and 0 x equal to 0. Show that if so Logishri, can you please try? Logishri, I don't know. You are not responding. Why do you have any issue or any confusion, or do you have any doubt in the entire thing? Please let me know because you are not responding at all. I have observed this from the second or third live session. Please let me know do you have any confusion, any doubts, because it seems that you are not responding at all. Okay. So yeah. So consider this function fx is equal to cos 1 by x, x is equal to 0, and 0 exponential. Show that this f is continuous. I mean, sorry, is it is not. We need to show that this f is not continuous. So using the sequential criteria, we need to show this. So Logesh, can you please try and please let me know. As I wait for 1 2 minutes, please try and let me know how to approach or please at least try to get the sequence in order to use the sequential criteria. Okay, so basically what you need to do, you need to find a sequence xn which converges to 0. Okay, because here our okay. So look, please try, Logesh, please try. You're not responding at all. So I shall wait for some minutes. Please try, let me know. Okay. Okay, so you are responding. So okay. So let me tell you how to do this. So also x is equal to, so then x is convert 0. So what is f of x and f of x and is equal to cos 2n pi, which is always equal to 1 because this is nothing but equal to cos 2, right? So we give see what we see that this sequence fxn goes to 0. Fxn goes to 1, which is not equal to f of 0. So if not actually, okay. But observe one thing that except 0 point f is continuous. Now, but observe if is continuous anywhere except, why? Because cos is continuous. Cos continuous and x to 1 makes continuous for all x not equal to 0. Okay. So yeah, so consider the following problem. So suppose if the function f2r and satisfy, sorry, f plus y is equal to fx plus f for all x unknowns, and f is continuous. X should prove that f is continuous at every c belongs to R. So basically, what I am doing, suppose so the question is if the function are R and if satisfy the additivity. Given that if it's continuous and 0, we need to show that if it's continuous at every c belongs to R. Okay, so so the viewers who are going to see this video through over YouTube, so please try it for 1 or 2 minutes, or else, and then I will tell how to solve this. Okay. So just obviously, just so well. So one thing is that obviously here you need to use the sequential criteria of continuity. So the hint is the following. In the sequential criteria continuity. Okay. So you you try for some minutes. Then I shall tell you to approach this. Okay. I shall get back after 2 minutes. You please. John of the database. Okay, so uh, hmm. So yeah. So well, so it can be done as follows. So yeah. So basically, the if is continuous for every c means we need to check limit h goes to 0, f of c plus h is equal to fc, will it hold or not? Okay. But what is given? But given f is continuous at 0 means the limit h tends to 0, f of 0 plus h is equal to f 0, which is nothing but 0 from the condition. Now, so basically f of c plus h is equal to f plus fh. So limit h goes to 0, f of c plus h equal to fc plus limit h goes to 0, fh, which is nothing but fc plus f0 is equal to fc. So in this, so we can show that this function is continuous everywhere. Okay. So this is the first part of this solution. Moreover, prove that. Moreover, prove that. Prove that fx is equal to some kx for all x belongs to R, and for some k belongs to R. Okay. So well, so this is not usual way to. I mean, this problem is some kind of tricky. So let's do. So let's see how to solve this. Okay. So first we will check it for sort of integers. Basically, first we check the natural numbers that are positive integer. So choose the belongs to it. So what? F of n is equal to f of 1 plus 1 plus dot 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 plus 1. So by the condition, this will be n f 1. So, and this hold for all n belongs to n. Okay. Now, choose m belongs to z, m less than 0. Then minus m belongs to n, right? So, f of minus m is equal to minus m a1, right? But observe that if m minus m, this is obviously f0, which is nothing but 0, and this is equal to fm plus f minus m. So this implies of f minus m is equal to minus fm. So this gives minus fm is equal to minus mf1. So this implies fm is equal to ff mf1 for all m belongs to n. Sorry, for all m belongs to z. This is the first part. Okay. Now we need to show this for the continuity, for the rational values. So choose the x equal to p by q from q. So this implies, and well, so here we assume without loss of generality, assume q is greater than 0. Okay. So this gives what? This gives P is equal to QX. So this implies what? If P is equal to uh, QFX. Okay. But if P is what? If P is equal to PF1 is equal to QFX. So this implies Fx is equal to P by QF1 is equal to Fx1. X into F1. So, sorry. Excuse me. So till now, so Fx is equal to Xf1 for all lengths belongs to Q. So now we need to show that this also holds for let's say irrational values. Okay. So choose an y from choose a y which is irrational. Okay. So yeah. So they are into the sequence xn in Q such that xn goes to y. Okay. So if xn goes to f1 by continuity of f, what is fxn? So fxn is equal to xn f1, and this goes to yf1. So by uniqueness of the limits of the sequence, this implies fy is equal to yf1. So this implies what? This implies fx equal to xf1 for all x belongs to the reals. So this is what we need to show. We want to show. Sorry. Yeah. So yeah. Okay. So this is for the viewers who are going to see this video over the YouTube. So please go through the uh, solution once again. I shall wait for 2-3 minutes. Okay. Then we shall go to the next problem. Okay. I shall get back after 2 minutes. Okay, so Logan, do you have any confusion? Okay, so I don't think you have any confusion. So, okay, so the next problem is that, sorry. Yeah. So, next problem is the following. Suppose if it's a function defined from 1 to r, defined as follows. F(x) equal to x point x, sorry, x belongs to rationals inside 0 and 1, minus x belongs to the rational limits. Show that, first show that f is injective on 0. Secondly, show that f assumes every, sorry, real numbers on 0 1. That is, we need to check if it's surjective. Thirdly, show that f is only continuous. X equal to half. Oh, so let's do it one by one, okay? So, so how to check if it's injective? So, choose point if x1 and x2 and assume if x1 is equal to fx2. Now, if both x1, x2 belongs to q or q complement, then obviously x1 equals to x2. And if without loss we should assume x1 belongs to rationals and x2 does not belong to rationals, then this thing gives x1 is equal to 1 minus x2. The point is left side is a rational value and right side does not belong to rational. So this inequality can't hold. So basically, if x1 equal to x2 equal either both x1 equal to both x1 and x2 are rational or both are rationals. So this automatically leaves x1 is equal to x2. So f is injective. So now we need to check the surjectivity. Okay. We need to check the actual surjectivity over 0 and 1 because we need to show that if assume the value of a real number of 0 and 1. Okay. So take r belongs to 0 or 1. If r is a rational number, then f of r equal to r. And if r doesn't have a rational number, f of 1 minus r is equal to 1 minus 1 minus So this 1 minus 1 minus r is equal to r. Okay. So, so if basically 0 1 to 0 1 is bijective. Okay. So the next thing, what is this? So yeah, so we need to check continuity at 0. So let x, so let f be continuous at x. So there are a sequence of rationals and a sequence of irrationals such that Rn goes to x and Rn goes to I. Okay. Then f of Rn goes to fx and f of Rx Rn goes to fi. Okay. Now since Rn rational, so this is basically small Rn and f of r, and I mean sorry, it's a mistake. Rn goes to x and In goes to x. Okay. And so this gives f of In goes to f of x. But what is f of In is 1 minus In. But Rn goes to x and 1 minus In goes to 1 minus x. So but uniqueness only means x equal to fx is equal to 1 minus x. This implies x equal to half. So if we assume that this is continuous at x, this directly tells us x equal to half. So x is only continuous at half. Okay. So yeah, this was the one problem. So the next problem is the following. Yeah, so yeah. So consider the following, sorry, consider the following exercise. One second. For example. So consider function f r2r. Find on the formula. Fx equal to x, x belongs to q, and 1 minus x. Rational. So identify the points of continuity. So how to do this? So like as the previous solution, here also we need to use the sequential criteria argument. Okay. So how to do it. So, so, so take x belongs, so let f be continuous at x. And so we need to find such all possible x, okay? So we will get a sequence Rn and the sequence of irrational Rn converging to x, okay? So basically, so if since we have so by the assumption, so fx n goes to frn goes to fx and fin goes to fx, okay? So what is frn? Frn is equal to 2rn because rn rational, and what is fin? Fin is equal to 1 minus I, right? So basically 2rn goes to 2x and 1 minus in goes to 1 minus it. So uniqueness of the limits 2x equal to fx equal to 1 minus, and this means what? X equal to 1/3. So in this way you can find the points of continuity of f. I mean of this type of functions. Okay. So this is the one technique actually. So Nagashuri, can you please go through these last two solutions and please let me know do you have any confusion and doubt because you are not responding at all. Okay. So please go through these last two solutions, last two examples, this one and the bottom one. So please go through it and let me know do you have confusion and doubts. Okay. As well wait for some minutes. Okay, so it seems that you have no doubt, or I don't know what happened. You're not responding at anyway. That's no big deal here. So yeah, so yeah, so come to the next problem. Okay, so I hope that you don't have any doubt. So consider the next problem. So so consider the function if R2 are defined by fx is equal to x squared plus 1 whole cubed, and this is x when x is irrational. So same question here. Find points of continuity of f. Okay. So how to do it? So just one second. Okay. So oh, one second. Probably my traffic travel. Sorry. One second. One second. Yeah. So it's simplified. So how to do it? So let C belongs to R and assume f is continuous at C. Okay. So we'll get a sequence. So we'll get a sequence of rationals and the sequence of irrationals. Such that Rn goes to C and In also goes to C. Okay. So by our assumption, if Rn goes to Fc and if In should goes to Fc. What is Fn? Fn is equal to R square plus 1, and what is Fn? Fn will be just In. So, but I mean, so R square plus 1 goes to x square plus, sorry, c square plus 1, and In goes to C. So, Uniqlo's limits c square plus 1 is equal to Fc is equal to Fc. This implies what? This implies c square minus c plus 1 equal to 0. So, c is equal to 1 plus 1 over 2, which is not a real number at least, right? So basically, f is discontinuous everywhere. Okay. So so let me just f r to r, and we have assumed that f(x) belongs to plus 1x, and with x belongs to rational, x belongs to irrationals. Then we need to find the point of continuity of f. So if we choose a c, then if it's continuous at c, if Rn is rational, In is rational, such that Rn, comma C, Rn goes to Rn and In both converge into C. So by the same process, we finally get the fact that c square plus 1 should be equal to C. But this gives us C is not a real number. So if it's discontinuous everywhere, okay. So Logically, please go through the solution. Please let me know during confusion. I shall wait for 1 or 2 minutes. Okay. So yeah. So it seems that you don't have any questions actually. So okay, so going to the next question. Okay, so yeah, so there is something known as the local property or neighborhood property of continuity. Okay. So this property is not sorry. There is same issue with the graphic driver. I'm very extremely sorry for the inconvenience. Sorry. One second. Okay. So this is known as the local property. What is known as a neighborhood property. What is this tells? This tells that I believe that the site has already done this, but just for the sake of recall, I think it's better to recall this term again. So then tells that suppose I be an interval and let if I to R be continuous on I. Let's say belongs to I. Now if C is equal to 0, this term if FC equal to 0, then there exists suitable delta greater than 0 such that it should be delta greater than 0 such that frolics inside this thing, this incident I f of x is the same sign as ifs. So basically, this tells us suppose you have a function f, and suppose around this point this function is continuous, so there will be a small neighbor where the function sorry, I mean, suppose this point is function greater than 0, so there will be a small neighborhood around which the function remains to be get positive or negative. Okay, so I mean, obviously it's some I mean, obviously you can guess it, but it's a theorem and it's practically useful theorem. Okay, so yeah, so this is one thing. Okay, so now consider the following example. Oh, yeah, there's another definition of continuity which is equivalent definition. Okay, this tells that a function f d to r is continuous if and only if inverse image of any open or closed set of r. So inverse image of any closed subset of r will be open or closed. So this tells what? That a continuous if and only inverse of open set is open and inverse image closed is closed. That's the thing. Okay. So suppose how to do this? So well, so it's a theorem, and I believe the Sarah has done it. Okay. Anyway, so some example. So suppose AG are two are continuous. Show that the function x says that if x equal to gx is closed in R. So using the previous definition, try to show that this set x as an fx and gx agree are closed in R. Okay. So logically, please try for some minutes. Please at least please try. Okay. Uh, I shall I shall wait and then tell you how to solve this problem. Okay. Please try and let me know if you get any um, direction, if you get any answer. Okay. So yeah. So so in what sorry the graphic driver is. So take oh sorry. I don't know what the issue with my graphic driver. So choose X so choose H to be F minus G. Okay. So then Hx equal to Fx minus G. Okay. So what will be H inverse 0? H inverse 0 is equal to all those x are that Hx equal to 0. So x says that Fx equal to so I mean so this is basically the same x says that Fx equal to Gx. Okay. So so, but basically H inverse, but it's basically single zero is closed and H is, I mean, so this H is obviously continuous map because if it is continuous and some of the continuous maps are continuous, okay? So this continuous, so basically H inverse is zero, the closed set. So all those x cells that Fx equal to Gx set. I mean, sorry, it's a closed set. So in this way we can solve this type of problems, okay? Sorry, same thing. So Logan, should you please let me know the confusion or not? Okay, so I think it's always necessary to revise the things that has been done in a particular session. Okay, so first let's start first. So let's start the revision from the first. Okay, so before starting this, I shall wait for some minutes. Logically, if you have some issue or some doubt or some confusion with the definition or applications, please let me know. Okay. I shall get back to you. You can think about it for 2 3 minutes. I shall get back to you after 2 minutes. Okay. So, Laveshwari, do you have any question or confusion? Please let me know. Otherwise, we shall start revising things. Okay. So, let's just start the revising. So, wait, wait one second. So, first to start, we had to start with the definition of continuity. This means what? Suppose f is a map from D to R. We say this function is continuous at x belongs at x, which is a point in D. If for epsilon greater than 0, we can find a delta greater than 0 such that. What's it? So delta greater than, so if it's continuous, it will be continuous if for epsilon greater than, we can find a delta greater than 0 such that for any y in the epsilon neighborhood of delta, sorry, I mean if delta neighborhood of x, the fx minus fy is less than epsilon. So basically, function continuous means we can draw the graph of the function without breaking the continuity of drawing lines or curves. Okay. So, first example is that constant maps are continuous. So for constant maps, we have chosen epsilon. Well, one thing to note that in the definition of continuity, this delta depends on epsilon, but on case to case, I mean from in case of a particular function, any delta may work. But in general, delta will depend on epsilon. So here any, so choose any delta, actually any little word, choose any delta, and if we choose y to be in the epsilon neighborhood of x, then fx minus fy is 0, which is another epsilon. So if it's continuous at x belongs to t. Okay. So fx equal to continuous for x belongs to. So how to show that this identity map is continuous? So choose a y belongs to R. Okay. So now choose delta with epsilon, and if we choose any point y around the delta neighborhood of x, which is greater than the epsilon, fx plus fy is less than epsilon. So f is continuous at y. So in this way, you can show that the identity map is continuous. Right? That is is continuous. Okay. Can similarly we can show, I mean, using the fact the broader continuous will continue, we can show that x goes to x is continuous, and also similarly we can show that the x goes to kx, I mean some constant time into x is a continuous one. And as a matter of consequence, it tells that polynomial function are continuous. Okay. So there is one theorem, and this is one of the most useful theorem in the continuity. I mean, in order to prove continuity or discontinuity. But this theorem is actually used in order to show that some given function is continuous. Okay. So, so f d2r be a map, and suppose d is subset of r. Now, if f is continuous at c, okay, one second. Suppose and f is continuous at c. This if and only if equivalent to saying that if you take any sequence xn d converging to c, the sequence fxn goes to fc. This is known as the sequential character of the continuity. Okay. So, as a matter of application, we have first see this following implication. Suppose if the function r2 are given by x goes to 1, or x belongs to q, and x goes to, I mean, if x equal to 1, where x is rational, and if x equal to 0, when x is rational. So, claim. So, here we need to show that it is discontinuous. Okay. So, we have done? We have taken a x naught from real, and suppose, I mean, so by the density of rationals and irrational in R, we can find a sequence Rn rational numbers and In rational numbers. So Rn goes to x naught and In goes to x naught. That is, yeah. Now, since we assume that if it's continuous at x0, so the sequential criteria gives us that if Rn goes to fx and if In goes to fx naught. But if Rn is 1 because Rn irrational, and if In equal to 0 because Rn irrational, so 1 equal to 0 is a contradiction. So if is not continuous x naught, but since our x naught is arbitrary, so if is not continuous everywhere. I mean, if it's discontinuous everywhere. So basically, this is a nice application of the sequential criteria theorem. So please, so well, so the logically, the thing is that uh, there is no point to revise if you are not going to ask any question. Well, so right now, so yeah, so before going to the further examples or corollaries, let me know, do you have any confusion or any doubt till now? Okay, I shall wait for 2-3 minutes. Please let me know about this. Okay. So I hope you don't be in confusion. So, consider for example. So consider fx to be cos 1 by x when x not equal to 0. 0 when x equal to 0. Show that it is not, we need to show that it is not continuous at 0. Okay. So, so is a sequence that converging to 0. And so fxn is equal to cos 2n. So xn equals sequence converging to 0 and fxn is equal to cos 2n pi, which is 1. So basically, we see that, but but fxn goes to 0, which is not equal to, it's not continuous. So observe that one thing is that since cos is continuous and x goes to 1 is continuous for all x non, so the thing is that cos. So f is a function of R to R. So the next question is that suppose f is a function of R to R, and suppose f satisfies the additivity law, and assume that f is continuous at 0. We need to show that f is continuous if every c belongs to R. Okay. So here we need to sequentially try to continuity. So how to do it? So since f of c plus h equal to fc, I mean, since limit h goes to, I mean, so basically we need to check that if it's continuous at c means what? We need to show that the limit h goes to 0 f of c plus h is equal to fc. Is equal to fc, okay? So basically, limit h goes to 0 f of 0 plus h is equal to f0 is equal to 0. Okay. So, I mean, now we can use the additivity property of it. That is, if c plus h is equal to fc plus fh. And this gives that limit h goes to 0, f of c plus h is equal to fc plus limit h goes to 0, fh. And this tells that this fc plus f0, which is fc because f0 is 0. And so, okay, so the continued part is done. Now we need to, moreover, we need to show that this function fx will look like x. So how to do it? So we choose a natural number small n, and so fn is equal to f1 plus 1 plus 1, which is nothing but n of f. So we choose m below. So okay, Okay, so yeah, so we have first showed that Fn is equal to F1. So this thing is that this Fx equal to Kx holds true for F1. So this tells the Fm is equal to Mf1. So the relation holds Fx equal to Kx for all positive numbers, positive integers. Holds for rational numbers. So here we take num x. Yeah, so for a random rational numbers, x will be by q, and without loss of generality, assume q greater than. So p is equal to qx. P is equal to qfx. So ap is equal to what? Ap is equal to pf1. This is equal to qfx. So this implies fx is equal to p by q f1. So now p by q is x, so is fx1. So this tells, so this tells that the fact that fx equal to x1, this holds for rational numbers also. Okay. So now we need to show the rational numbers. So we use a y for a rational number. And so we get a sequence x rational numbers, so xn goes to q. Okay. So if xn goes to f of y. So what is fxn? Fxn because all xn are rationals. So x and f1 goes to y f1. So basically f of y is equal to y f1 with the uniqueness of the sequence. So this is what we want to show. So Lokesh, please once I go through the solution, let me know the confusion. I'll wait for 3 minutes. If you don't have any confusion, I shall move to the next problem. Okay? Yeah, those who have joined late, please. Okay, so actually, we are right now we are discussing this problem. So this problem tells that suppose if it's a function r and is satisfied f of x plus y is equal to f x plus fy. So it satisfies additivity condition, and it is given that the f is continuous or zero. We need to check that if is continuous every c belongs to R. So Ravi system joined late, so please go through the solution. I hope you know about this.
Yes, sir.
Yeah, so do you know about the sequential criteria?
Sir, sequential criteria.
Sequential criteria continuity. Do you know about sequential criteria of continuity?
Sir, if a function is continuous, then the sum of function is also continuous.
No, no, sequential criteria of continuity. Sequential criteria.
Sir,
Okay. So,
please recapitulate, sir.
yeah, one second. Okay, so first we have started to do with the definition of continuity. Okay. So so I hope you know the definition of continuity, right?
Yes, sir. At the neighborhood of point, the limit
Yes,
exists,
right.
sir.
Yeah. So there is something known as, then we have discussed some theorems, the constant maps, identity maps, and continuity. And then we have discussed the following theorem, which is known as the sequential criteria continuity. This tells that suppose there is a function from D to R, and C is a point from D. Then if it's continuous at C if and only for any sequence xn in D converging to C, the sequence fxn converges to fc. This is known as the sequential criteria of continuity. Okay.
Yes, sir. Okay. So, any sequence xn and d, then the whole sequence f of xn will converge there.
Yes, yes. Not only converge, it converges to fc. Right? Understand?
Sir, and the proof of this theorem?
I hope you have done this proof in the class, right?
Yeah, okay.
So then we have discussed some examples. So I will upload this PDF to the Google slide. You can go through it, okay? Since you have let George, it is possible to go through everything. So right now we are discussing the
Sir,
following.
when cos of 1 by x,
Sorry?
sir, once the continuity of cos of 1 by x,
Yeah.
cos of 1 by x continuity. Sir, just once glimpse.
Sorry, I didn't get you. So you are asking about cos 1 by x continuity, right?
Yes, sir. At 0.
Yeah. So basically, we directly use the sequential criteria in order to show that this function is not continuous at zero. Okay. So first target is to choose a sequence xn which converges to zero, but the corresponding sequence fxn is not converging to f0. Such a way, we need to choose a sequence xn. So we have chosen xn to be 1 by 2 n pi. So obviously xn converges to 0, but xn is 1, and which is not equal to f of 0 because f of 0 is given to be 0. So that's why this function cos 1 by x is discontinuous. Understand?
Sir, I didn't get this. Sir,
How do you get it? I didn't get you actually. What do you say?
sir, I did not get this explained.
Okay. So so the point is here we need to use the sequential criterion. Okay. So we need to come up with a sequence converges to a point 0, but f of that sequence is not converging to f0, right? Such a sequence we need to construct, right?
Yes, sir.
So we choose a sequence xn is equal to 1 by 2 n pi. Okay. So then this sequence converges to 0, but the sequence fxn is cos 2 n pi, which is equal to 1. But 1 is not equal to f0. So basically f of xn is not converging to f0. So that's the sequential criteria. F is not continuous at x equal to 0.
Okay, sir. Yes, sir, correct.
So so let's move to the next problem. This problem was like, suppose the function f r to r is a real world function over R, and suppose f is additive function, and given that f is continuous at 0, we here prove that f is continuous at every point in R. So Ravi, yeah. So Ravi, please go through the solution once. So please let me know, do you have any confusion? Please go through the solution, okay? If you have any confusion in any line, please let me know.
Yes, sir.
Yeah.
Yes, sir. Got it, sir.
Okay, so you have understand the continuity part. So moreover, using those assumptions, we can prove that the function f(x) is of the form kx for some k belongs to real. Okay. So first we have proved that first we have proved this holds true for the naturals. Then we have shown that this holds true for integers and then rationals. So please go through the solution once and let me know during confusion. Okay. And anyway, here you only tool is needed to be used is the continuity at any point and the f is additive. This tool you only need to use. Okay. Please go through and please let me know.
Yes, sir. Correct, sir. I will go. I will go through this. Please proceed, sir.
Yeah. So moving to the next problem. Okay.
Yes, sir. Okay. Sir, this example, can you explain once?
Sorry.
F of 0, 1 to R.
Yeah,
Sir,
yeah.
the
This
last
example.
example.
Yeah. So this so basically here f(x) equal to x and when x belongs to rationals and 1 by x to irrationals. Okay. We need to show the following. First, we need to check if it's injective. Then we need to check that if assumes every real numbers on 0 and 1. Then we need to show that if it's only continuous at x equal to half. Okay. So first, so you try the continue injectivity part and try and show that the if assumes every real number on 0 and 1. Just do it now.
Sir, it will be injective now on 0, comma 1.
Yeah, definitely right.
Uh, sir, through counter, I mean, through counter also we can prove this now through negation, like taking f of x1 equal to f of x2, and in the end we will come as x1 equals to x2.
Yes, yes, yes. Yeah, so that's the way of showing injectivity, right? So should I? So can I go to now the part three, or you are trying the part one and two?
Sir, please go through part.
Yeah, yeah.
Uh, Sir, once part 2 also explain.
Okay. So for the part three, one second. So in part three, we need to show that if it's continuous only at x equal to half. Okay. So we are choosing a random x and we are assuming that if it's continuous at x. Okay. So by the density of rationals and irrational, we can get a sequence of rational numbers and we get a sequence of irrational numbers converging to x. Okay. So, but since we have assumed that f continuous at x, so the sequence frn converges to fx and fin converges to fx. Okay. So if Rn is equal to Rn because Rn is rational, and if In is equal to 1 minus In because In is irrational. But then the uniqueness, but since Rn converges to x and 1 minus Ix converges to Ix, so the uniqueness of the limits x is equal to fx is equal to 1 minus x. So this gives x equal to half. So we'll start with the arbitrary x, assume that x is continuous, I mean if it's continuous x, and then finally get that x equal to half. So if it's only continuous, x equal to half. Okay. So you understood the solution?
No, sir, I didn't get this.
Okay, okay. In which point you did not get?
Sir, this only point, how did you get this? Half is the only
Okay.
point.
Yeah, okay. So first we start with the random x, okay, and we assume that f is continuous at this x, okay. So then we are trying
Yes, sir, correct.
sequential criteria. So Rn converges to x and In converges to x. So if Rn converges to fx and if In converges to fx. So if Rn is equal to Rn and if In is equal to 1 minus In because In is our irrationals. But this Rn converges to x because of our choice, and 1 minus In also converges to 1 minus x. So basically Rn converges to fx and Rn converges to x. So by the uniqueness of limits, x equal to fx is equal to 1 minus x. So this gives x equal to half.
Sir, this one minus I of Rn, is it given or what? The value of f of In.
So look at the function. Look at the definition of the function. It is f of x equal to 1 minus x when x is an irrational number. And we have chosen the sequence in from the set of irrationals. That's why f of in is equal to 1 minus in. Understood?
Okay, sir, correct.
Yeah. So in this way you can show that this f is continuous. Okay. So yeah, so today's time is over actually. So don't worry, I shall upload this PDF in Google Slides. Okay. So if you have
Okay,
any
okay, sir.
question, please get back to me in the next live session, which is going to happen in the next Saturday. Okay, 7 to 9. Okay.
Okay,
Yeah.
okay,
So
sir. Thank you, sir.
I'm leaving the call.
Yes, sir. Thank you very much, sir.